Hello, and this is lesson 1.5. Most important thing we're going to cover today is going to be the average rate of change. We're going to go over the Squeeze Theorem briefly, more of that in class, and limits of compositions of discontinuous functions. So it's a bit of a catch-all section. Again, I'm going to say that A rock, our average rate of change, is probably the most important thing. And you should recognize this formula because it's the same thing, ready, as a slope. And so, yay, you already know how to calculate such things. I will mention that when we're doing real world problems, we will often do stuff over time. And so hopefully that'll help you remember time goes on the bottom because of that phrase over time. Now, instantaneous rate of change is also the same thing as the derivative, and we are not covering that this chapter. Derivative right there, that's in the next unit. So we're going to touch on the concept briefly here. We're going to basically be calculating some average rates of change, and then we're going to sort of kind of compare it to being an instantaneous rate of change, meaning well, I'll get to it. So now I wanted to mention that I see that there's a spot here for us to write work. And you guys know that sometimes I do things sort of big. So I'm about to do it very large. But for those of you that just want to put stuff in your notes, these are your notes, okay? And Mr. Taylor's handwriting so gorgeous, everything looks perfect, and I think everything is pretty straightforward. But I want to cover it in a way that I think that my students are going to understand it, and so I'm going to do, my tried and true method right here. Everybody recognizes the f of x and an x table. Okay, so if I wanted to know what is happening when x is 2, then I'm going to plug in a 2. And if I want to know what is happening when x is a 3, then I plug in a 3. Okay, and so I'm just going to write all that work down, that I have something being cubed minus 2 times something being squared minus 10, something being cubed minus 2 times something being squared minus 10. And notice how I set myself up and then I plug in the number. I just want you to know, as a teacher, this is a tool that I use because kids can interrupt me in the classroom and I forget where I'm at, and sometimes I might get confused with the numbers. When you are taking a test like the AP exam, you might get stressed and you might find that you need, this sort of tool to help you as well. So it helps you organize your thoughts if you just write the equation down. And I'll mention there were definitely some students who, when they were writing stuff down on that first unit test, the unit 0, they did not copy it down correctly. So please take your time and be careful. Okay. Now here I'm going to say 2 cubed is 8. Oops, I wanted that in orange. 2 cubed is 8. And 2 times 2 times 2 is also 8, only it's negative. And then there's a minus 10. So this ends up being negative 10. Okay. Negative 10. The second one here, I'm going to have a 27, and I'm going to minus, ready, that 18, because 3 squared is 9 times 2 is 18. And then I'm going to minus 10, and what I'm going to end up here is going to be a negative 1. But I did break out for you the TI Inspire, and I just kind of wanted to show you how quickly you could do this. Ready? F of 3 minus f of 2, and the whole thing being divided by, ready, 3 minus 2. Boom, that slope will pop right out at you. And I just love that. So I hope that you do feel like using the TI Inspire from time to time. So we just calculated that A rock was, and here I did that really fast. So did you realize what I was doing? Ready? A rock, oh, not colon, equals M equals, ready, f of 3 minus f of 2, all of that over 3 minus 2, and y, because this here is x sub 1 and y sub 1, and whoops, I meant to put those in orange. There you go. And the other one, this is x sub 2, and this is y sub 2. And so now you know where that all comes from, and you know how to do it. And if we were doing it by hand, we would have put, ready, the green number, -1 in front with a minus sign, and then we would put the orange number inside of some parentheses because it came along with its own minus sign. And 3 minus 2 on the bottom. The negative of a negative is a big fat positive. You see me do that all the time. 10 minus 1 is 9, and 3 minus 2 is 1, and so that's how we got a 9. Okay, but I did like the calculator better for that. So then we want to do the average rate of change of f of x between x equals 3 and x equals 4. And you see the pattern that we kind of have going here. So I could say down here that I have this point 4, and then I'm going to plug in a 4 being cubed minus a 2 times a 4 being a squared and minus a 10. And the number that I get there is a 22. And now when I think about, doing these two things, my A rock is slightly different, right? A rock from 3 to 4 on the x-axis will look like this. The slope is, ready, it's f of 4 minus f of 3 all over something minus something. And what are those two somethings? Ready? So 4 and 4 and 3 and 3. And so if I was going to hop over here, I could just grab that and I could change every number to be the number that I want it to be, right? Those are 4s and these are 3s. And I just think this is so handy. I wanted to make sure that I showed it. Ready? Boom, I get 23. So over here, I'm going to calculate that to be a 23. So will you ever need to do a slope by hand, like without being allowed to use a calculator on the AP exam? Yeah, sure. But there's at least a whole third of the test that you can use a calculator, so you might get lucky. Okay. So now that I've done this, I found an A rock equals 9, and I found an A rock equals 23, and I want to move back over here. So this one was 9 and this one was 23. It says which of these is likely to be a better estimate of what he's calling instantaneous rate of change. So when we look at a slope and we say we have an endpoint and we have a beginning point and we have an end point and we calculate the slope in between them, everything is really kosher, right? Everything's good. I know that I'm going from one moment in time to another moment in time, and that we're changing position and we're trying to figure out, how much did we change our position over that time. Instantaneous rate of change is where I want to imagine being able to take a single point. I'm trying to underline that. A single point on a curve, a single point in a real world equation where just exactly at that moment, I know exactly how things are changing. And so when I talk about instantaneous rate of change, I want you to immediately start thinking about the gas pedal on your car, because that is the speedometer measures the change that you are putting in when you press that pedal. So if you want to go 20 miles per hour, then you press the pedal down until you see that 20. That 20, that's my instantaneous rate of change, right? That's how I'm changing at that moment. And when you see that dial moving, that's the kind of thing that I'm thinking about. Okay, so which of those two examples is going to be a better estimate of my instantaneous rate of change? Well, first of all, this thing isn't changing very fast, right? This first one, 9, that's not very fast. But here, if I'm changing, say these were seconds between second 2 and second 3, and I've moved 9 units, I don't know, feet, meters, whatever, miles, if we're talking about rocket ships. Yeah, really, in a second, it could move many miles. Okay, once we get out into space, things start moving really fast. If you want to get to the moon or if you want to get to Mars, we're talking really fast. So if I'm moving, say, 9 feet per second, that is not nearly as much as 23 feet per second. So I want to know exactly how fast I'm going at every second because I'm an astronaut or I'm an astrophysicist. Well, in that case, then I'm guessing that if I want to know what's happening at 2.4, 2.4 is somewhere in between 2 and 3. So I'm going to say between 2 and 3. And right now, we're just using the average rate of change. But there turns out there is a formula that I'm going to be able to use, and it involves a really amazing algebra trick. And when we calculate it, we'll be able to find out exactly somewhere between 9 and 23 how fast it is that things are changing at that second 2.4, right? So anyway, let's just do some more practicing with average rates of change for a while. And it says the data in the table shows the mileage from the start of a 4-hour car trip recorded at 1 hour intervals, and assume that that car continued in a same straight line. So I've got my time in hours and I've got my miles from the start. So when you're first starting things, in this case, let's say that it's a brand new, I'm driving it right out of the factory. There were no miles on the speedometer. An hour in, there were 55 miles on the speedometer. 2 hours in, there was 120 miles on the speedometer. Not on the speedometer, the odometer, my bad. The odometer is the one that measures how many miles the car has traveled total. So 3 hours, that was 180 miles, and 4 hours, that's 250 miles. So if we're going to find the average rate of change for part A, which is the average speed of the car for the final 2 hours of the trip, I'm noticing then that I'm starting at hour 2 and I'm going to hour 4. So, right, those final 2 hours are the last 2 hours. Now, why don't I start at 3? Because, in my second hour, when it finished, I was at 120 miles. So then if I count another hour, that would be my second to last hour. That would be 180 miles. And then if I count another hour after that, right, that's my fourth hour in the car, it finishes at 250 miles per hour. So there's a little bit of trickiness when we count. And if your brain hurts here, I want you to think about the example that I'm going to talk to you about in class, which is about birthdays, okay? So find the average rate of change in the final 2 hours of the trip. And I'm going to say that my average speed is the same thing as an AROC, an average rate of change, and that I can say that I have 250 miles minus 120 miles, and that this is 4 minus 2, and this trivial as work. I find out that my answer is 65 ready miles per hour, and I definitely want to include units because on the AP exam, units are worth points, and if you do not put the units down, then you lose points. So you can pass the AP exam and not answering every question, but going in and making sure that you write the units down for every answer and then just answering a few of the questions because the points, the number of points they give you for units, it's significant. Okay. So estimate the instantaneous speed at the 1.5 hour instant. And I'm going to say, well, in that case, maybe between hour 1 and hour 2 would be exactly halfway, right? 1.5 hours is in between those 2 points. So my AROC for this, my average rate of change between hour 1 and hour 2 is going to be, ready, 120 minus 55 over 2 minus 1. And so I end up with, again, 65 miles per hour. Isn't that interesting? Okay. And here he says in his notes, he says that this is my speed at the 1.5 hour is approximately equal to 65. I don't know that that's exactly true. I know that it's close. It's close to 65, but it might be more than that. Okay. It might be less. So for part C, he says, during which hour does the data suggest that the car reached the greatest instantaneous speed? And that's a little bit more tricky, okay? So here I want to just kind of add this note that speed is approximately equal to, but it's not instantaneous speed, okay? It's like an average speed. So I'm going to write the words average again, and that it's approximately equal to. If I wanted to find out the exact speed, I'm going to use instantaneous, and that's going to be next chapter. All right, so then how about this last piece? I'm going to look at these points and I'm just going to mention something right now. Okay. So I just kind of want to think about this. Going from 55 miles to 120 miles, I'm pretty sure that this is just that 65 miles is how far you traveled in that 1 hour. And that from going from 120 miles to 180 miles, that I only traveled 60 miles in that hour. Maybe you saw a cop, for a minute, and so you slowed down a little bit, just while the cop was in your view. But going from 180 miles to 250 miles, that hour, I picked up some speed. Okay, so I noticed that I was going slower in the hour from 2 to 3, and so for that last hour, from 3 to 4, I picked up my speed and I went an average of 70 miles. So I'm going to say that between 3 and 4th hour is when my speed was the greatest. Okay. And by the way, I'll also mention something that you can always look for the steepest slope on a graph. We don't have a graph right here, but there are definitely some graphs coming up. And wherever you see that the slope is the steepest, that's how you know that the distance from one moment in time to the next moment in time, that if you're traveling the highest vertical height, that's when things are going the fastest. Okay, so the squeeze theorem is also known as the sandwich theorem, and it says that f of x is less than or equal to g of x, is less than or equal to h of x, that if you have that being true, for all values in some interval containing, a particular value, which I guess we'll call C, and that if you set up the limits at C and you look at f of x for C and you look at h of x for C, that what you should be able to see is that if those two things are coming ready to the same number, then that inside function will also be coming to that same number. So you might want to rewind and hear me say that again. Okay? Informally, if a function g is squeezed or sandwiched between two other functions with the same limit, then g will also approach that same limit. That's a nice way of putting that. Here I have two graphs, okay? And this graph is the orange graph at top, and this graph is the green graph, which is on bottom. And I see that they are both approaching the origin, okay? So I would say then that the limit of f of x is, as we approach 0, is going to be 0. And the limit of g of x, as we approach 0, is also 0. So there you go. Let's write that down. This one equals 0. Sorry, I'm supposed to write them in the wrong colors. This one equals 0. And hey, that one also equals 0. I can see that they are approaching a height of 0. Right there. That's my height. This is the line y equals 0. Okay? So now let's take a look at number 4. It says the graph of that third function, and we're going to call it k of x. And I'm going to make it pretty. Look at how pretty it is. Purple. Ooh. K of x is shown along with the two functions from example 3, and we're saying that if g of x has k of x sandwiched with it, with f of x on the other side, then we can find that limit. Ready? The limit as x approaches 0 of k of x is going to be 0, and this is how we say why. Ready? By the squeeze theorem. Ta-da! Now there is a very famous squeeze theorem use, and that's for the function y equals sine of x over x. And I'm going to give you guys a video to watch from the lovely Nancy Pye on this issue to help us really, get a handle on that. Okay, so in the meantime, use the functions graph to find the following limits, and I have f of x and I have g of x, and these are two graphs. I notice that there's a jump discontinuity right here, and that there is a hole right there, and so they're not continuous. So I just need to make sure that I'm careful when I'm plugging in numbers, and I'm checking very carefully. For example, when x is 3 and I look at 3, whoops, I should erase that. When I look at 3 on the x-axis and I trace up, I will find that I am also at a height of 3. So on top, when I evaluate f of 3, ready? It looks like this. F of 3, and then I square that, what I end up with is 3 being squared, because the height that I was getting at 3 just happened to be 3. All right, so how about the second equation then? So what is g at 3? So here's 3, and I'm going up to here, and I'm over to there, and it's 2. So I'm going to calculate g of 3, and then I'm going to add 1 to it. So I get a 2 plus a 1. And what I end up with, when I'm all said and done, is 9 over 3, which is 3. And that's my answer, okay? Now, the limit of the next piece then is I want to evaluate g, and I'm using green here, but I want to evaluate it at some number that I get from the output of f. The output of f at 3. Well, what is f at 3? Well, remember, it just happened to be 3. So now I want to evaluate g at 3. Oh, well, I already did that. G evaluated at 3 just happened to be, ready? A 2. So that is my answer. It is 2. Now for this last one, we've done so many things with 3 that we just slow down and make sure you're doing it carefully, okay? What was G of 3? What was G of 3? I don't remember. Here, let me finish my writing. I'm going to take the value that G was at 3, and I'm going to find that value, and then I'm going to evaluate F at that value. So it's like input to output, okay? So G of 3, let me come over here and double check. Hey, G of 3 was 2. So that means that I take a 2, and I'm going to plug it in to F, and now I'm going to find out, well, what is F at 2? So F at 2, oh, well, it was also 3. I mean, that was a very boring function, so there you go. If your brain hurts, I don't blame you. We're actually going to do a Khan Academy practice on this, okay? So the Khan Academy will help you a lot with that. And that is the end of your notes, guys.